The title of today's webinar presented by Michael Hubenthal from IRIS is More Modern Seismology in the NGSS Classroom. It's beyond earthquake locations. Go ahead and advance one, please. Go ahead, one more, please. So following the webinar, we'll have time for Q&A. If you want to, throughout the webinar, please drop your ideas and thoughts and questions into the chat box. We'll be keeping track of that. And I think we'll stop a couple of times during the webinar to respond to a couple of those questions. I also want to point you to upcoming webinars. We have one more webinar in our 2019-2020 webinar series that's planned for May 14th. And that will be a webinar on the If-Then Ambassadors Curriculum Connections that come from the Lyda Hill Philanthropies and the American Geosciences Institute. I invite you to join that webinar. It will be a discussion of the materials out there for the If-Then STEM ambassadors, which feature 4 wonderful STEM ambassadors in geosciences and across other sciences. And then also, if you're looking for something fun to do and binge watch over the summer, it's never too late to go back and watch some of our previous webinars. So bit.ly/webinar NGSS will get you to the archived pages for all of those webinars. This is the end of our 5th year, so quite a few of them, and you may want to go back and take a look at some of those. Go ahead, please. So again, please feel free to type your questions and ideas and thoughts into the chat box as we go through the webinar. I'm going to turn things over to Michael Hubenthal at this point. Thanks for joining us, Michael.
Great. Thank you very much. I appreciate it. And I'm really pleased to be able to come back and give a follow-up on more modern seismology for your NGSS classroom. So before we get started too far, I want to say this is a follow-on to a webinar that was given in February. However, I've sort of set this up so that it follows on but doesn't require that you had participated in the previous webinar. However, the first slide, I'm going to just kind of review back to a few ideas that I talked about. Basically, if you want to know more about those, I'd suggest you maybe go back and take a look at that webinar and the slides that I used there. That'll provide more details for anybody who's interested. So one of the places that I began this sort of discussion was, what's going on with NGSS and sort of our standard earthquake activities that are commonly done in our classrooms. And of course, the most common one that we see that deals with seismic waveforms is this idea of locating the earthquakes using an S-P calculation, and then having students draw circles on maps. And in the previous webinar, I talked a little bit about some of the concerns with this in light of the NGSS. So the first one, of course, is that NGSS standards don't explicitly include the process of locating earthquakes within them. Though earthquake locations are used as a part of a number of the performance expectations, the actual process of locating is not included. The second thing is that the S-P location method is really out of date. This is a pre-1960s method for locating earthquakes, and there's an overemphasis on finding the final point at which the approximate epicenter is, based off of the image that you see here. Right, so students really begin to focus in on getting circles to cross rather than understanding maybe why this process works. And then we get into some of the technical difficulties that we run into. In order to make it work for students, we often end up having to sort of compromise the science that's going on. So fake data is commonly used. So we have wiggles that are highly simplified. Seismic waveforms now are comprised of 3 components of motion: vertical, north, south, and east, west. And in these activities, we commonly see a single component of motion, and it turns out to be hard to pick a P and an S wave on the same channel, so all horizontals or vertical. And then finally, we're using flat maps for what's actually a 3-dimensional solution. So students are often frustrated that their circles don't cross, but one of the main problems is that we're putting this onto a flat map so we can print it for students in front of them, and they run into some problems. The other thing that I see commonly being done is the calculation of Richter magnitudes. And again, this is a dated method, right? We're no longer using this. It's only applicable to the California region because it assumes seismic wave velocities in the crust that are comparable to the California, and they require amplitudes as measured on a very specific seismograph, which is a Woods-Anderson seismometer. And this is no longer produced and really only used in for sort of long-term monitoring purposes historically, so we can make comparisons between past records to modern seismometers. So these are some of the challenges that we run into with these traditional earthquake activities. And so my goal in the talks have been to point out, oh, I forgot one more thing. I'm glad that this popped up. And I didn't mention this in the previous one, but we also have an issue with vocabulary. So the S-P approach is commonly referred to as triangulation method. But it turns out that this is really how we locate mobile devices using cell towers, and triangulation is based off of measuring angles here that we see on the right side of the screen. When we're doing S-P, what we're actually doing is taking part in a process called trilateration. So this is using these radiuses of circles in order to find a common midpoint or a point of intersection. And this is the actual S-P process. So again, number of concerns with some of the things that we've been doing traditionally for seismology in the classroom. So I came up with a list of initially 3, and now I've expanded it to 4 options for what teachers might consider doing in their NGSS classroom. And option 1 that I went through in the first set of talks was that you might consider dropping earthquake locations and replacing these with a more aligned activity using seismograms. And so we have an activity where students can use seismic data from a recent event, and they can determine the core of the Earth and measure the dimensions of the size of the core of the Earth using seismic waveforms, and they can model wave velocities as well. And so works at the sort of, middle school, high school level. And it's something different that students can do with seismograms that is more aligned with what we know about NGSS standards and performance expectations. The other piece that I would note is that option 2, and we got into this in the other talk, was, maybe if you really do want to do earthquake locations, we've got ways now that we can update that process to help students understand how we actually locate earthquakes. So we might start off with a simple method called a bisector location, where students are looking only at P waves, and then we can use that to build students' understanding to get into a more iterative approach to using P wave locations that's more similar to the way we actually locate earthquakes. And so these 2 methods are tools that IRIS is currently building out right now. We have functioning beta versions of those. We haven't released them yet for the public, but we expect to be finished with those, either late spring or into the summer, so people can come back in the fall semester and begin to maybe change the way they're teaching earth locations. Option 3, and I think this is an important one and a nice expansion of this that kind of came to me as I was talking with some few folks online about this idea is, if you really want to do trilateration, I think the idea here is just updating where we teach it in the geoscience curriculum. And so there's a great application here. GPS uses trilateration, and it's something that we could have students doing in the classroom if we really want to teach this process. They're using 3-dimensional spheres as opposed to circles on a flat map, but it's actually the exact same process. And so I just included a couple of links here that people might want to take a look at. One is here online that has an actual tutorial for a lab that a student might do. And then UNAVCO, excuse me, has some really nice demonstrations that you can see being done here on the image on the right, where they can find points in space by using this exact same process. So I'd recommend people maybe go ahead and take a look at those as options for maybe continuing the processes that they're already doing in their classrooms, but maybe applying them to a new area. So the 4th option, and what I'm going to focus most of my time in this talk on today, is about how we might use seismology when working towards non-traditional performance expectations. So I couldn't help but include this as an example for us to look at. If we want to have some really modern examples, maybe we need to be thinking about how seismological measurements can provide evidence for a variety of different things. And in this case, I chose one of the middle school standards that performance expectations that we might take a look at. This one says, construct an argument supported by evidence for how increases in human population and per capita consumption of natural resources impact Earth systems. And so, as we look at this, we might say, well, can seismological measurements provide evidence that are impacting the Earth system? So here's a little bit of data that we might take a look at. So this is from a former student of mine that's at Caltech currently. And this is taking a look at seismic background noise levels for Los Angeles. And so I'd ask us to examine this plot. Some of us might not be used to looking at this sort of data. So let's take a look at the the X and Y axes. We can see that on the right-hand side of the plot, we have, on the left-hand side of the plot on the Y-axis, we have ground displacement, and we're measuring these in nanometers. And on the X-axis, we have time going from right to left. So I'd ask the group to maybe take a look at this carefully and what do you see in this data? What are people seeing? We can use the chat window for this. Great. There's some really good responses showing up into the chat window. And I think it's, people are on track with this. One of the places that I sort of wanted to start was, when we're working with students, taking a look at this data, it's worth taking a little bit of time to say, what's the scale that we're actually talking about here? And so ground displacement in nanometers, we need to kind of put that in context for people because this is a unit that people probably aren't used to thinking about. So seismometers are super sensitive instruments. So when we're looking at this, we're saying how much is the ground moving? Well, if you look before 315 and that plot, we were seeing peaks at approximately 1.15 nanometers, and post we're seeing about 0.75 nanometers. So to give us a sense of scale, 1 nanometer is 1/1000th of a micron. And we know that a human hair is roughly 100 microns thick. So we're talking, about very, very, very small changes in the displacement of the ground that we're able to detect here. So really small. However, what I think is worth noting is, when you calculate the percentage of change, this is on the order of 30 to 40% decrease in the amount of change that we're seeing here over time in terms of seismic background levels. So, we kind of have this steady threshold up here at the top. I'm going to try to write on the screen and see how this works. Let's go to, maybe this will work better. Yeah, so if we look here, some of the patterns that people noted were these daily changes. So these are daytimes up here at the peak and the middle of the night down here at the lowest cycle. So we have these very daily cycles. And then you'll notice we have larger patterns where we go from weekdays to weekends and weekdays back to weekends. So we have a couple of different kinds of signals that are appearing here. And we begin to know that our signal kind of breaks down here right in this area as we have some changes. We go into a weekend on the 15th. And when we come back into the week, we have some significant changes that have happened here. And so a number of you correctly pointed out that, could this be due to COVID-19? And yeah, over this weekend of 315, this is where the CDC started to ban large gatherings of people. And so people were definitely starting to stay home more. And then we get into this sort of new normal of lower seismic noise, and you'll notice that the first 2 weeks were at one level, and more recently we're seeing even lower levels. But like you, I was very interested in the spikes that were also appearing here, and wondering a little bit about, what those spikes might be. And so I did a little looking online. So how might we tease this out? How could we figure out what these spikes are? See if I can get rid of my pointer back to chat. So, one thing that way I handled this was I went on to the news and I said, okay, so what's going on here? Well, people are going out into public more at this moment. And by using a quick Google search, for example, I went out and found that on this date, this is the 19th of March, this is when the governor of California put in place the mandatory ban on the mandatory stay home orders. And so I think what we're seeing happening here is people immediately going out to the grocery stores to do some shopping, to get errands, and that sort of thing. And we're seeing that in this spike in traffic that we're getting. Now, these other ones, I didn't take time to go look at them, but I'd be really curious to see what we could find because they are such large spikes that are interesting as to what might be going on and causing this noise. I would note that it could be something local to that particular station, potentially, but it's probably a larger pattern, part of a larger pattern. I can't figure out how to get rid of my. Okay. Sorry about that. I was having trouble getting rid of the laser pointer. So let's maybe move forward to the next slide here. So, when we think about this in terms of the standard that we wanted to address, I'm going to go back. We're asking, can we construct an argument supported by evidence for how increases in human population and per capita consumption of human resource or natural resources impact Earth systems? I think the question that I get when I think about this is, okay, so how does this seismic noise impact Earth systems? Is there something going on here? Is it polluting our environment? Is it? Okay, I'm seeing some interesting ideas coming in now into the chat. I see a suggestion of air quality showing up, right? And so I think that when I think about this, I would use this as an engage activity, right? I would think about this as a way to seismic data is really providing evidence that human behavior has changed in response to this policy and to the virus itself. So we have responded, and then we can use this change in behavior either as a decreased consumption, right? We're buying less stuff, we're using less gas, or we might think of it as a proxy for decreased human population. So if we were living in normal times and we had less people, we might also have the environment acting like it does now. And so where I might lead students with this activity is I might say, okay, well, let's go in and take a look at how, what else might change. And I think we could have students brainstorm, a wide variety of ideas that they could then begin to investigate on their own. And so we might think of things like air quality was mentioned in the chat. We might take a look at things like noise pollution or water quality, all of which I think we would begin to see a few examples of how we might use seismological techniques and seismic data to sort of address a performance expectation that we might think of traditionally as being more of an environmental standard or environmental science type of performance expectation. And certainly something that would be non-traditional in terms of thinking about our seismology unit. So at this point, I want to take a few minutes to pause and allow people to maybe make a few notes, jot down a few ideas, or ask a few questions about using this kind of seismic data to look at human behavior and also think about addressing this sort of standard. And while people are thinking, on the right-hand side, I will note that this is a similar plot of seismic noise, and this is from Brussels. We see this phenomenon all over the world right now. There's lots of plots that you can find online from Spain and a variety of different locations.
So hey, Michael, one question kind of came up in the chat that you might want to address while people are thinking about that. If it had been activity along a fault, would the signal look any different?
It's a good question. And in this case, no, it wouldn't look any different. You know, this is LA, and so we're, you know, we're in a heavily faulted area. You know, this is such a small change in ground displacement that it wouldn't have any real impact on, you know, sort of the forces that are acting on that fault. And the same thing would be true for places that are like highly volcanic. You know, these forces are so small that they're really not going to have any impact. One of the ways, though, they do impact the study of things like faults and volcanoes is because the Earth becomes significantly more quiet than we're used to. And these provide fantastic opportunities for seismologists to basically get cleaner recordings of events with a lot less sort of anthropogenic noise being recorded in them or over top of them. And so less filtering needs to be done. The other opportunity for seismology is that it also provides a way for seismologists who use the noise. So there's ambient noise tomography studies where people are using this background noise as part of their research. They're then able to correlate the signals they're seeing with the ambient noise because now it's been removed. So we can have a way of verifying sort of what they're filtering out of their data on a regular basis to be sure that it really is ambient noise and it's not other things. So it does provide some unique opportunities for sort of the more traditional seismology studies. Okay, let's maybe move on to another example that we might want to look at. So this was an example that I did give briefly in the previous presentation, but we touched on it so quickly that at the end that I wanted to make sure it got some time of its own to have a look at. So what we're looking at here on the right-hand side of the screen is a plot of ice quakes. So Greenland has quite a few seismometers placed on it, both in the center of the Greenland as well as around the edges. And the plot shows the thickness of ice overlain with red dots that are ice quakes. And many of these are stacked on top of one another. So we tend to have these areas of seismicity or ice quake seismicity occurring in very localized areas. So the question we might ask is, you know, what's shaking in Greenland here? And the performance expectation that we want to be thinking about is analyze geoscience data to make a claim that one change to Earth's surface can create feedbacks that cause changes to other Earth systems. So in this activity, you know, we're going to begin by thinking about, well, what might be causing all this shaking? What's going on that's causing these ice quakes to take place? So I'm seeing a few comments coming up in the window. I see comments about movements of the glaciers, maybe day and night signals. Let's see, magma injection, global warming, calving of the glaciers. Right, so we have two pieces of information that the students are going to really be looking at here. They're going to be looking at, ideally, spatially, where these earthquakes take place. Calving of the glaciers certainly is going to head to that. We know this is at the edge of the glacier where we're not gaining ice. But we might also look at this long-term pattern in this frequency of the earthquake. So how many are occurring per year? And so, we could make a number of arguments about what might be going on. Temperature increases come up several times. People have mentioned global warming. And so, I would say, well, what data would help you narrow that down? If we wanted to test that hypothesis for temperature increase, what would we need? Yeah, I'm seeing position of the glacier fronts over time up here. One thing that we might want to do, I see correlation with temperature. Yeah, one thing we might want to do is, okay, well, what if we didn't have temperature? We could maybe look at this in a different way. What if we took the same data set and we sliced it by month? And so we know we're in the northern hemisphere, so we said, okay, well, what if we looked at this, bin the data, this is between 1993 and 2010, what if we bin this data and we said, okay, when are ice quakes happening? How does this influence your thinking that we previously had? Yeah, we're seeing these peaks that are taking place in July and August, probably our warmest months. So this is going to support the idea. I like the way this was stated here. It's going to support the idea of a relationship with temperature, right? And this is maybe important to think about because the other, if I go back one slide, oops, the other piece that somebody might be able to argue is, well, maybe we just put more instruments on the glacier. Greenland, if you were to go back into the seismology literature, you wouldn't see a lot of instruments on Greenland going back. So maybe we're just recording a lot more smaller earthquakes or ice quakes taking place on Greenland because we've got more seismometers on the island. And that's completely possible. But then when we look at this data, it certainly begins to say, okay, well, something is going on here. So let's take a look at two data sets. On the left, we'll have this original data set of number of ice quakes per year. And then here is the average annual air temperature in Greenland over time. And again, this is a great place for you and your students to begin to have a conversation about correlation and causation. These two plots certainly don't mirror one another exactly, but the trends are certainly the same. And we know from a variety of other studies that we do have a lot more melting and calving and fracturing of the glaciers as a result of warming air temperatures. So this is an example, again, of another way that we might think about using seismology to address a number of different topics that maybe we wouldn't traditionally think of seismology having anything to say about. Similarly, we can also see this same pattern, this overall warming, in terms of looking at sort of background seismicity of the whole world. So the noise that we looked at in the beginning section of this talk, we can see that the overall amount of ambient noise has been increasing with time. And that correlates well with increases in the amount of wind globally, and that correlates to climate change as well. So we can use seismology to measure some of these things and begin to see feedbacks between different systems. So how are one system being influenced by another system, and then in fact using sort of non-traditional techniques to sort of get at these sort of interfaces. And I think this is an exciting area of science and one that certainly fits well with the NGSS. So if people want to get access to this activity, you can find it in two places. It's on the CERC website. It's part of the exemplary collection on CERC, but we also have it available on the IRIS internship, or I'm sorry, the IRIS website as well. And so people can download that, that activity from there. So that I'll leave that up for just a second. And at this point, I wanted to, again, pause answer some questions, give people a chance to sort of maybe take some notes, or post a question or a comment into the chat.
Michael, we had a question going back to the first data from Los Angeles, and it was from Dodge. Dodge is asking how small earthquakes, he's watching small earthquakes from magma injection in southwest Iceland, and how that might help to reduce the background noise and improve the quality of that data.
Yes, exactly. That's exactly right. And so he's right about that. So the less noise there is, the data will, those small background earthquakes will be more visible during those quiet times. There will be less filtering that they need to do in order to see those. So again, we might, depending on the data sets, some of the automatic flagging tools that people use, where they're template matching waveforms, they may be able to automatically begin to detect smaller and smaller earthquakes. And so the frequency of events might go up.
Michael, we have a question from Ed.
Yeah, I'm looking at that now. Yeah, so Ed's saying, can you think of any data that could be presented to students that would correlate, but for which there isn't a causative relationship, just to reinforce causation, or just to reinforce correlation with the shaking, I mean? Yeah, it's a good question. And I think that in this case, this was an example where it was correlation for a long time. And I think what it required was then somebody to develop a model for how this could be happening in order to explain it, right? And so, in order to go to that causation, you need some sort of model that explains the processes that would be going on to make it happen. So I don't have an example right off the top of my head where we could see just correlation but no causation, other than some good memes that I've seen about pirates online, about the increase of the number of, or decrease in the number of pirates and climate change and some things like that, that seem to correlate as well, that are just completely nonsensical. All right, so let's maybe go to another idea. So along a similar lines, I would ask this group, so would you be surprised if a magnitude 5+ earthquake occurred where you lived? And secondly, you might think about, what if it occurred in Oklahoma? And the important piece here is less about whether you'd be surprised, but more about why you might not be surprised. So here we might begin to take a look at a variety of data. We're going to examine this particular performance expectation, construct an explanation based on evidence for how the availability of natural resources, occurrence of hazards, and changes in the climate have influenced human activity. And so, people are saying, let's see, I'm looking in the chat, some people would be surprised. I'm seeing a little bit of posting about hydrofracking in the thread. Yeah, so a number of good notes in there about so a variety of speculations. But in the big picture, thinking like a student, most of the time we talk about students in earthquakes, we're talking about plate boundary earthquakes, and very little work about or discussion about intraplate seismicity. And so in this case, students might be very surprised to find that for a period of time, the hazard in Oklahoma, Texas, was equal to or greater than California for some of these sort of mid-sized events. And so it would be worth maybe taking a look at and potentially surprising to some. So again, I'm going to show you some data from an activity that's worth taking a look at and asking some students some questions about what's going on here. So the primary plot on the left-hand side of the screen is going to show the number of earthquakes per year, and across the x-axis we're going to see the year of those events. And there's a pretty strong overall pattern here that we see. Over time, we see a steady increase, or a steady increase, and then a significant increase in the number of earthquakes that take place. And if you look into the notes of this plot that are written into the middle of it, we can see that we not only are the number of events going up, but the number of significant events are also going up. So basically magnitude 4s and greater, which are big enough to be felt and do damage, especially in an area of the country that wouldn't traditionally be used to experiencing earthquakes, is going up quite high. And then on the right-hand side of the screen, I'd encourage you to take a look at sort of spatially what we see happening, right? So lots of earthquakes taking place, and they tend to be a little bit geographically located, or they seem to be. So in order to sort of make sense of this data and what's going on, we normally in this activity, we need to have a little bit of a discussion about the development of a horizontal hydraulic fractured natural gas well. And so we have a strong increase recently due to the price of natural gas changing to going on to this developing this technique that has been around for a long time, but being used much more commonly. Some of it has to do with the ability to drill horizontally and drill more of these wells to then break up the rock. But again, the keys here for the point of this talk are really around, we're using a lot of water here, right? So we're going to use a lot of water, and then we're going to pump it down into the ground to break the rocks, and we're going to pull it back up when we get the natural gas out. And then this fluid that comes back to the surface has been altered. It's got a lot of, it's highly saline, might have a little bit of radon associated with it because there's a lot of flowback groundwater that comes with this when we drill down and break up the earth. And so I'm sort of doing this in a very shortened time frame, so I'm not going into a ton of details here. But again, the key here is that we're generating a lot of water. And through this activity, we are bringing students around to see, okay, well, there's another piece of this. It isn't just hydrofrac wells. And in fact, to Ed's question earlier about correlation, in this activity, we actually show the locations of the hydrofracking wells to earthquakes. And they definitely overlap one another, but the pattern is maybe a little less clear. Certainly not one-to-one for the hydrofrac wells. So then the other piece of this that I'm showing a figure on here on the right is that the green on the far right-hand side of the screen is a production well. And so we're getting rid of this wastewater by disposing it into very, very deep wells that go much deeper than our production wells. And we're using high pressures to basically push this down into formations that are less tight, have more pore space in them, to get rid of this water. And so, again, for the sake of time, I'm going to kind of speed up this entire process for people. But we would normally have had students take a look at where these injection wells are located relative to earthquakes. And again, they are going to overlap one another, but they don't correlate super well. They're not a perfect one-to-one because there are some injection wells where we're not seeing a lot of earthquakes. And so this is more of an example where we have more complex processes going on. We begin to see that what we're actually correlating well with isn't so much the location of the disposal wells, but a stronger correlation with the volume of water that gets pumped down those wells. And so this was a paper that came out, I guess it actually came out in 2017. That was the first one showing this strong correlation between events, particularly large events shown with stars in the plot, and the color was on the plot showed the cubic meters of wastewater that's being injected. And so where we have red is where we're seeing some of these really large events taking place. And so when we think about this, the other piece that the activity gets into, and I didn't include a slide here today, but we have to have a mechanism for this. So we get students thinking about what they already know about earthquakes and how this idea of injecting large volumes of wastewater into the ground would affect what they know about the causes of earthquake. And we do some modeling with the earthquake machine to sort of illustrate how this might occur, sort of what the physical phenomenon might be. And so by then, you now have developed this model for what could be going on. We have data that shows a strong correlation. And so it gives us a way to begin to sort of bring about an explanation. And so the final piece to this activity, I think I have the next slide. Yeah, so the final piece of this activity then would be to say, okay, well, let's look at the end of this data. What do we notice about the pattern of the data? We have this steady increase, but then we have this strong drop in 2016 and then an even stronger drop in 2017. So how might we explain this sudden decrease of earthquakes in Oklahoma? Yeah, one guess is economics, right? One is new regulation. Did production go down? Gas prices fell. Yeah, these are all great examples. So, you know, if suddenly it weren't so economically feasible for these companies to be producing natural gas out of these wells, we would have less wastewater to get rid of. But in this case, what happened was beginning late in 2016 and then into 2017, the Oklahoma government began to put limits on the amount of the cubic volume that you could discharge at any one time. And so they were still discharging high volumes, but they were changing the rate at which they were discharging it down into the ground. And so if we think about the forces that this would put onto fault systems, you know, we can assume that the stress is changing less rapidly. It's having more time to sort of dissipate as that fluid flows away. And so that's going to have a smaller impact on the faults and the likelihood of having an actual slip event occur or an earthquake. And so again, I went through this really quickly in a short time, but this activity gives students a chance to explore a topic that they maybe are used to seeing, earthquakes, but in a completely different way. So how are we using this topic of earthquakes as part of our investigation to convey sort of how it impacts people? And in this case, the reverse is true because prices went up, people wanted more natural resources, and there can be some side effects from these collection of natural resources. So a couple of resources I would point out. This lesson can be found at this URL, but there's a lot of good information on fractracker.org that I think would be worth taking a look at in terms of some of the mapping tools that they have available. So I'm going to pause for a few questions that people might have, or people might want to take a few notes, or think about how this might fit into what they do.
Michael, this is all reminding me of very early on when we started to implement NGSS, and everybody probably dove into it and said, oh, which of my favorite activities are still in the DCIs and which are gone. And, and now thinking about things in a more maybe sophisticated way to say, wow, there are all sorts of new questions that we can ask that cut more broadly across many of the sciences, but also incorporate social science, and just kind of wondering what you think about how, as a community, we spread that word a little more broadly.
Yeah, it's a really good question. And, I think that in some ways, my immediate answer, just from having, just recently been involved in some conversations about changing what's going on in the classroom, change can be really hard. And in some cases, it means giving up things, activities that people have been used to doing for a long time. However, I think that it offers, I think the message for those people are that we have exciting new opportunities to present science in a different way. In this particular activity, what I really like about it is this idea that we look at the data, we develop a theory about what might be going on based off of the data, but the theory itself isn't worth anything if we can't develop an explanation, a physical explanation that could be causing that. And then we need to get some data that supports our theory. So in this case, the idea had been posed, we see this change. Everybody was rushing to say, yes, it's hydrofracking that's causing this. Turns out to not be hydrofracking, right? We said, okay, well, clearly we're putting this down into the ground and we're changing these faults. But it turns out that the mechanism wasn't quite as they initially thought. It actually turned out to be this wastewater injection. And so I think that looking for ways to both convey content, but also emphasize those processes, things like models, are really important in this sort of new NGSS era. And so we're looking for ways to communicate that.
So kind of as a quick follow-on, we have a question about whether there are any kinds of structured pedagogies that are being built in as you're developing the lessons, any pedagogies that you're thinking about really building lessons around?
Yeah, so this activity, and I didn't mention it here, but this particular activity is built around argument-driven inquiry. So I know ADI has a whole bunch of books that are available through NSTA, through the NSTA bookstore. This activity I actually wrote, I've got 2 ADI activities that we wrote for IRIS through some professional development work that I was doing with the folks who developed ADI. And these are available online. I don't think there is an earth science book available. There's physics, chemistry, biology, I think, ADIs. But I think, using this pedagogy gives a chance for students to look at sets of data, ask questions of that data, and put it together in a way that's meaningful. So if you're not familiar with argument-driven inquiry, one of the really powerful pieces for me when I work with students using the ADI approach, and I would say it is a structure to lots of things that good teachers have been doing for a long time, is they all have these experiences to investigate the data, draw conclusions from it, and then as a teacher, we sit down and talk about the content once the students have lots of experience with the data. And that creates hooks that really enrich the conversation that you have with these students, because they all have had a chance to get in, monkey around with the data, get messy with it, play with it a little bit, so that when we begin to think about the content that we're trying to convey, that all plugs back into what they did. So in this particular case, ADI is one that we used here. But you could do it without doing an entire full ADI. They tend to be pretty long. You could do mini versions of that for sure.
Michael, I'll just mention that there is argument-driven inquiry in Earth and Space Science from NSTA Press, and I'll stick that in the chat.
Okay, great. That's great to know that it came out. I know they'd sort of been working on it, but it seemed like it had gotten hung up for a little while. So I'm glad that's out.
Yeah, Victor Sampson is the lead.
Yep. Okay, so here's another example. Again, we're going to starting to get close to the end of the presentation time, but I'll just sort of mention this one briefly. One of the other traditional ways that we might use or earthquakes in our classroom is to talk a little more about forecasting earthquakes. So the location of events, earthquake locations, is common in most middle school earth science classrooms. We look at the maps of where earthquakes take place. We might look at the depths of them and the magnitude of them, and we may define plate boundaries. However, if we go into that data and use it in a slightly different way, we can begin to address performance expectations like this one. Analyze and interpret data on natural hazards to forecast future catastrophic events and inform the development of technologies to mitigate their effects. So this activity that we're not going to spend a ton of time on, other than to point out that we're using this same data that you've probably looked at many times in your earth science classrooms, but instead we're going to take it into Excel and we're going to just sort it by magnitude bins. And so by simply taking a region of the world and investigating how often bins of magnitude events occur, we can begin to create something called a Gutenberg-Richter plot. And this tells you, whoops, this is a semi-log plot, so students might need some coaching on how to interpret a semi-log plot. But what we begin to see is, excuse me, how many of these earthquakes are occurring, say a magnitude 5 occurring per year within a given region. So we might look at, say, within California, the green line, we can say that we have X number of magnitude 4.5s that are taking place in California, and we can compare, how does that compare to places like Italy or Indonesia or some of the other locations that students might want to investigate. And so this is a great way for students to begin to collect this data, manipulate this data, and then begin to engage in the process of discussing earthquake forecasting. For example, while we might ask students to think about, well, what would it mean if I extrapolated these lines? Could I say California hasn't had a magnitude 8? Could I extrapolate my line all the way out to a magnitude 9 or a 10? What would that mean, and what would that look like? So it's a slightly different take on a traditional activity that you can do with your students in the classroom and get them really working with some data in a quantitative way. And so it's another good one. And an obvious tie-in to that would be, again, really modern seismology, gets into this idea of shake alert. So shake alert is a system that's being developed in California that detects the P arrival from earthquakes. And when it detects that, it's able to develop use ways to get people safe. And so for people, that would be practicing things like drop, cover, and hold, moving away from hazardous areas. But what Shake Alert does, it's integrated into sort of some of our automatic systems to do things like stopping trains, aircraft at runways, pausing surgeries, a whole variety of things that maybe we haven't considered before. And so this fits really well with some of the performance expectations around generating and comparing multiple solutions to reduce the impacts of natural earth processes on humans, right? So how else might we think about how some of these activities or these activities could influence and save lives? We do the building activity, and that's a great starting point. That happens regularly. But we have a variety of other activities that we might do. And so this one, we don't have a formal activity built for this yet, but this is one of the areas that we're looking at developing into the future. And then there's lots of others. And I'll sort of pause here and take questions that we might look at, because I realize we're about to the end at this point.
I invite people to drop any more questions that you have into that chat box. I think we've kind of exhausted what was in there. I'm kind of wondering, I'm starting to see organizations like IRIS putting out new offerings for summer for PD. I'm wondering if you guys are talking about that, given the scenario that we're all living through here.
Yeah, we are. Some of that has been taking a look at, we weren't able to go to NSTA, for example, this year and develop a lot of our in-person ones. We have thought about developing some of our new activities with a lot of associated videos. And so we've recently begun to add step-by-step videos that are essentially virtual professional development to some of those activities. So for example, the earthquake machine activity that we've done lots of PD around and have a couple of labs built around. If you go onto the website now, we've added about 5 different video clips that sort of walk you through how to do the activity. And one of the nice things that those videos allow us to convey is sort of why we do the things that we do in the activity, you know, how we might sequence one activity versus another. This one comes first because we're trying to build up a concept that we're then going to use in the second activity for students to understand. So yes, adding some new videos. Some of that for us has been a change in thinking, okay, our videos don't have to be super professional. They really just need to convey the content in an efficient manner for teachers to make use of them, as opposed to, you know, going into a studio and making something that looks really fancy. I think that, you know, one of the outcomes is we're all getting much more comfortable with seeing each other in a little more casual setting, and that's probably a good thing.
And I think that many of us are experiencing schools around us that are really pushing forward their efforts to get devices into students' hands. So maybe there will be more students for next year. They'll have devices that they can access all of this great data and these great tools. So I think there's a good opening for PD there. Go ahead, Carla.
Yeah, I'll just mention that Iris produced some wonderful short videos that we will be suggesting you binge watch from our virtual conference that happened on Saturday. Also, it looks like Mitchell has put the survey link in the into the chat. So please be sure to take a couple of moments and complete that survey. And we do have a question from Randy.
Yeah, I'm looking at Randy's question. So 2 questions. One, Dodge asked one a little bit earlier about magma injection related earthquake activities. We don't have anything on our website right now about that. That I can think of off the top of my head. Though you could investigate that with the IRIS earthquake browser, which is the event tool that I was looking at just a minute ago. You could probably use that to zoom into areas and get pretty small earthquakes, the types that you would probably see related to magma injection events, depending on what area of the world that you're looking at. And related to Randy's, yeah, this is an area that we're interested in growing. So developing more simulations and interactive models is definitely the way we're headed. The tectonic plates model from Concord Consortium is super. I think it's fun to play with. I love it a lot, and I would highly recommend it. So one of the things that we are developing now is sort of like a virtual earthquake that we would think of as being an updated version. So how do we actually locate earthquakes? And that would be sort of directed like virtual earthquakes. So we've got a few things along those lines that we're headed into, but it's an area that we'd like to develop sort of more of.
Before we lose everyone, maybe we want to move to the next slide. Thanks. Aida, you're muted if you want to talk.
Thank you, Carla. So the only way you can get this certificate of participation is by completing the post-webinar survey. So please do go to that link and complete that survey. We really do value the information that you share with us there. Next slide, please. As we said earlier, upcoming webinars, May 14th will be If Then STEM Ambassadors Curriculum Connections from the American Geosciences Institute and the Lyda Hill Philanthropies. And then please binge watch our previous webinars over the summer at bit.ly/webinar NGSS. As I said earlier, also, this is going to be the end of our 5th year of webinars in this series. And the webinar series is brought to you by 3 organizations, which are shown on the next couple of slides. Next slide, please. the National Association of Geoscience Teachers, which has a full webinar series. I encourage you to go to nagt.org and look at the webinar series there. Lots of interesting webinars, including an entire group that is now thinking together about suddenly teaching online. Next slide, please. Carly, you want to talk about NESTA?
Sure. The National Earth Science Teachers Association also offers a number of webinars, we partner with various different organizations, including NAGT, but we also did a number of elementary school-oriented webinars with NOAA, and you could find all of our webinars on this page here.
Next slide, please. Ed, do you want to unmute and talk about AGI?
Sure. I'll just mention that the American Geosciences Institute has a number of resources, not so many webinars, although we do have a very active YouTube channel, webinars separate from these, I would say. But the other thing is, between Earth Science Week and a product called Education Geosource, there are also a wide range of online activities and resources available for educators in all settings. So I would encourage you to take a look at that these days too.
All right. Thanks very much. And then the next slide, I think, just has our contact information. So thank you very much to everyone who joined us today, and thank you very much to Michael Hubenthal for a wonderful presentation and answering all of our questions. We appreciate that very much. Please look for registration information for the May webinar coming up in about a couple of days. Watch your inbox for that. And thank you very much to Mitchell for stepping in for Andrew in the background and working for us on CERC. Thanks a lot. Hope you have a great day.
Thanks, everyone. Appreciate it.